Good morning. How are you? No, my camera was messed up. There we go. Whoa. Okay, that's better. Okay, good morning, everybody. How are y'all doing? Let's see here. Let's get this open. Ooh, I'm close on time here. Okay, let's see here. Mm, well, okay. Okay, so it looks like it's time to start. Welcome all. Good to see y'all. And I guess we'll just kind of dive in here. Let me share screen. I will make a quick reminder to y'all about the homework. Just want to make sure everybody remembers that the homework, the first homework assignment is due today. And you can see it once I get my screen set up here. You can see homework 1, due date today, right? Further, don't forget what is assigned is all of the content syllabus exercises for these sections, right? The ones that are in the cells grouped together for homework assignment number 1. Okay, so 1-1 through 1-5. Another quick reminder while we're at it. Don't forget, I strongly encourage that you start working on the exercises and plan to finish them as soon as you possibly can, right after we finish those sections. So a lot of y'all did that. I'm comfortable, but just in case you didn't, section 1.1, right? We finished that last Wednesday. And so those exercises should have been started last week and hopefully mostly finished last week. And again, don't forget you got office hours and help room and the other instructors' office hours, etc. Not to mention, strongly encourage that you work in groups. Okay, so all that said, don't forget 11 o'clock tonight. Make sure to upload your stuff to Gradescope. Okay, let me pause just in case someone has a question before we get to the actual math. Oh, I see that someone's got a hand raise thing. Go ahead. You don't need to wait for me to recognize you. Just start talking. And I'm not hearing anybody. Does somebody have a question? Let me unshare. Let's see. Let's see. Oh, okay. You're still muted. Hello? Did you have a question? Maybe not. Okay. Well, you may be having technical difficulty. Anyway, let's dive in. If you do think of your question, or if you figure out your microphone or what have you, feel free to interrupt and just start talking and let me know what your question is. Okay. All righty. Oh, I see something in the chat. Let me look at the chat. Oh, yeah. Okay, exactly. Very good. Okay, we'll hope to hear from you in a minute. Sharing screen again. Here's where we were last time. We were talking about matrix multiplication. This again was hopefully a reminder of what you already knew from Math 218. But I do think this is important to make sure you remember that this is not just kind of a computational alternative that's not very good. It's not really the point. The point is that this relates the operation of matrix vector multiplication to a different construction about which we know different things and which has different uses, right? And so this is a reinterpretation. This is the opportunity for us to connect thoughts in different, more powerful ways. So anyway, make sure you're comfortable with that. And then we talked through this last time, as I recall. Yeah, pretty sure we did. In this section. And so, this feature called linearity is just really powerful. Now, why is it powerful? Pretty simple appeal. Look what you can do with functions that have this property, right? The mere fact that the algebra, right, is like, wow, you can just move linear combinations inside and outside the function. Well, my gosh, that opens up a huge amount of possibilities of stuff you can do. And when you can do stuff with algebra, you tend to prove results and get properties, and math happens, right? So why are linear functions important? Because we can prove theorems about them. Right? And of course, y'all have had a course in linear algebra, so I won't go further on that. And a bunch of examples. And then last big result that we talked about, when you're talking about Euclidean functions, in that context, linear is synonymous with, you can represent it with a matrix. Proof we went through last time is a nice argument. And furthermore, let me note for the record, not only is this a proof, but this is a formula for how to find that matrix. And the columns are the images of the standard basis vectors. That's the way I like to remember it myself. The columns are the images of the standard basis vectors. Okay, I'll review. So here's where we left off, and I will go ahead and comment on this as well. And this too is a linear algebra fact, right? So this should be a Math 218 thing, but in the sense that linear transformations correspond to matrices, for Euclidean, right? But for every linear transformation, there's a matrix. For every matrix, there's a linear transformation. In that sense, composition of linear transformations corresponds to matrix multiplication of the corresponding matrices. Okay. So there's different ways to see this, different points of view you can take and how you develop matrix operations. Side note, for whatever it's worth, I like to take, when I teach a linear algebra class, I like to take this as the initial motivation and arguably definition of matrix multiplication. You can see how that's reasonably easy to motivate, right? I mean, pretend like we didn't have any operations on matrices at all. We know that matrices represent linear transformations, and well, what should it mean to compose those? Well, golly, it feels like it really ought to mean that we're multiplying them. So I think that's a reasonable point of view to take. But anyway, okay, pausing. Okay. Just another quick reminder. There's a lot of linear algebra in section 1.6 that I did not just talk about. Do make sure that you're clear on all of that. I mean, all of 1.6 is fair game. I'm just talking about the stuff that, again, I think I can help the most on. And I think this either because it's the most important or because it's the most likely to be unfamiliar or, something along those lines. Okay. So that's all good stuff, though. Yeah, question?
Yeah. So I believe under this section 1.6, you have some examples.
Do I?
And yeah, a little further down.
Oh, yeah. Right.
What's the difference between that first one and second one other than just switching letters?
The first one is a dot product, and the second one is a cross product. Yeah. So what these two statements are saying, you might, if you want to speak it casually, you might say dot product is linear and cross product is linear. And then when you say dot product, it's implied that you mean, fix a vector and use that in dot product with that vector to define a function, and that function is linear. Right.
And is that just because of the distributive properties? And
yeah. That's right. It's because of the algebraic things that we know about these operations. These operations have good algebra, and algebra is the requirement that we have to check if we want to use this term linear. So yeah, totally. Yep. All righty. Okay, so on to section 1.7, new stuff. I don't expect that you've necessarily seen any of this. And this is the first part of the first section in the book, I'll say, in which I think it's likely that you may not have seen it in Math 218. so now we get to kind of the what you might call the normal part of the course. Okay, so new coordinate systems. We are going to find basically alternatives for rectangular coordinates. And now I'm sure you know what rectangular coordinates are. You might not have used the term, but if you have a point, right, then you can kind of drop down there to find the x coordinate, and you can slide over there to find the y coordinate, and the x and the y then make an ordered pair that are what we typically actually just call the coordinates, right, of that point. Okay, we're so accustomed to them as to not even think that that's a choice, but to think of that as just being, that's just what it is. But it's a choice. This is a coordinate system, and we're going to see some others in a couple seconds here. So before we go on to those other coordinate systems, I want to recognize certain features of rectangular coordinates. Again, just kind of seem like, well, isn't that just, it just seems like what it ought to be. I mean, of course, but we need to recognize that these are features. These are not, fundamental truths. These are not axioms of how stuff has to work, right? So in particular, these coordinates are unique. There is exactly one x coordinate for a given point. There is exactly one y coordinate for a given point. Well, I'm sorry to say, that is not going to be the case in these other coordinate systems that we're going to talk about, polar, cylindrical, spherical. It's not true. So yeah, it's true of rectangular coordinates, and get ready to let go of that comfort. There's some algebraic conveniences. I'm a big fan of this one, that when you're talking about, when you're in rectangular coordinates, that the coordinates are the coefficients in a linear combination of the standard basis vectors describing that point. That's a really nice fact, right? That's algebraically very useful. In fact, we've already made use of this several times so far in this course. So this is a peculiarity of rectangular coordinates, is not true for polar, cylindrical, or spherical that we're going to talk about in a minute. And then related fact that you can, in fact, this is really arguably, anyway, closely connected, kind of the same thing, really. But when you're taking a linear combination of vectors that you're describing with rectangular coordinates, you can describe that linear combination's coordinates by the exact same linear combinations. Well, isn't that luxurious, right? This is, again, something that we kind of take as a given. It's not really true in these other coordinate systems. So be careful. All right, so let's dive in. Polar coordinates. You know what? Some of y'all probably have seen this, but anyway, I'm not going to assume that you have. So polar coordinates, if you want to describe the location of a point, some point somewhere in the XY plane, polar coordinates say, instead of dropping down to there and sliding over to there, instead we're going to think about that angle we're going to call theta. And by the way, it's understood that theta is always measured off of the positive part of the x-axis, and positive thetas go counterclockwise. That's an arbitrary choice that got made long ago. So that defines a direction. If you have somebody chooses a theta, that defines a direction from the origin like that. Now, once you have that direction, then we can talk about how far to go in that direction. And we use the letter R to represent how far to go in that direction. So, well, here, let me do it like this. Let me do about like that. So that says, I'm trying to avoid using the word distance, but how far to go in that direction. Now I'm avoiding the word distance because R doesn't have to be positive. The word distance is an intrinsically positive thing. There's no such thing as a negative distance, right? And R does not have to be positive. So it's awkward to think of it as a it's misleading to think of it as being a distance. So let's recognize that it could be negative. And if it's negative, then how far are we going to go that way? If it's a negative, how far? Let's just go backwards. Right. So once you've got your direction defined, positive R's are over there and negative R's are over there. Okay. All right. Now, I like to think of this as a function. I think this is really, it really makes sense that, given a theta, well, the theta defines the direction. Given an R, well, the R says how far are we going to go? And between the two of them, that defines a point. That's a point in the XY plane. And we say that the polar coordinates for that point are these numbers. Okay. And the algebra of that is a pretty straightforward argument. Notice that you can make a little triangle here. Right. And so it just boils down to trig. And here's the formula. Easily argued that X is R cosine theta and Y is R sine theta. Okay. All right. So again, now I think it's useful to, remember that when we talk about polar coordinates, then, don't forget geometrically what these things are. R and theta they define, a direction and a how far. But algebraically, bam, right? That's extremely terse and precise. So these formulas are what really define R and theta. Okay. Now, again, keep in mind, we don't have these luxuries that we had up here for rectangular coordinates. And we're very quickly going to see right here, first thing, that they are not unique. So I'm just going to show you the for example. Let's suppose we've got some value theta, slightly positive, whatever. Well, that value theta defines a direction, right? Measure it again counterclockwise from the positive part of the x-axis. And now let's think about a value of R. Here I've got 5. And so we go a distance of 5 in that direction. And that gives me, let me do this in different color. That gives me a point. So you can think of these numbers as being the polar coordinates of that point. But awkward, check this out. That same point, if I were to go an extra pi of angle, an extra pi would mean a half turn. If I were to let my angle do a half turn, well, now I'm going, if you will, exactly the wrong direction. Well, if I were then to say, okay, well, then I want to go -5 in that direction. Well, negative again means go backwards from the defined direction. So instead of going this way, I just go that way by 5. And well, check it out. I get to exactly the same point. So that's the lack of uniqueness. You see both of these give us the same point in the XY plane. So different polar coordinates for the same point in the XY plane.
I'm sorry, could you repeat why we're going in the same direction, although it's -5 and not +5?
Yeah, so that's the deal with R. If you have a negative value of R, then you just go backwards from the defined direction, whatever direction is defined by your angle. So if our direction is that way, And if I want to, how far do I want to go in this direction? Well, I want to go a negative amount in that direction. Well, that would mean going a positive amount the other direction.
Okay, but so shouldn't we have a different value for the angle then? So,
Yeah, we do. Oh, yeah, absolutely.
oh,
So
okay, so it's the same point, but like two different ways to define it.
exactly. So
Oh,
these polar coordinates over here have they have a different theta and a different r. Right. Absolutely. Is that good?
yeah, thank you.
Yeah. Sure. No worries. And by the way, you can keep going. So if you go not just an extra pi, but if you go an extra 2 pi, then of course that takes you all the way around. And so now this value of theta and that value of theta, well, they point exactly the same direction. So not only do that and that get you to this point, but so does that. And then you can go another half turn, and you can see this is going to kind of stair step around, and it's just back, and all of these coordinates give you the same point. So wildly not unique. This is just life with polar coordinates. This is what it is, and it's a downer, right? This is a bug. This is a negative feature of polar coordinates, but polar coordinates has other positive features, and so we have to live with it. Okay, now a quick warning. Very often, and including our textbook, people are a little sloppy when they're writing down polar coordinates. And so you take, for example, you could write 2 comma pi over 6. And if you write 2 comma pi over 6, that pi over 6 kind of looks like an angle. And so you might think, oh, that must mean r comma theta, right? And so you're kind of guessing, though, that the person means, oh, I'm telling you this angle and that r. But the thing is, those numbers are real numbers. X could be 2. Y could be pi over 6. Pi over 6 is a number, right? And so maybe you're talking about that point, and these are different points. Right. So frustrating. But really what I would say here is this is just something to be aware of. It's a clarity problem, right? And so be clear, right? Now I remove all of the ambiguity just by saying r comma theta equals, right? Easy to do. And now I don't have to worry that I'm going to be misinterpreted. Okay, so heads up. Okay. How do you convert backwards? So we know how to solve for x and y if you have r and theta. Easy trick. Well, this same triangle here, you can try to solve for r and theta. And unfortunately, something bad happens, and you end up with these equations, not hard to write down, and then you're tempted to say, ooh, I could totally solve for r there. It's tempting to say, ooh, I'm going to take a square root of both sides and do this. But unfortunately, if you claim r is square root of x squared plus y squared, you're claiming r has to be positive, which it doesn't, right? So you just algebraically, you cannot solve this equation for r. You can't do it. And likewise, if you give into the temptation to say, oh, okay, well, I'll take arctan of both sides here, and we'll say theta is arctan of y over x. No, it isn't. Arctan is always between negative pi over 2 and positive pi over 2. Theta has no such constraints. You can't do that either. Again, there's a strong lure to try to solve for r and theta in these equations. Resist that lure. If you do, you're writing down likely falsehoods. Okay, so here's an example. We got a point here, x comma y is -1, -1. And of course, you can take this and plug it into there, and out comes very quickly that we know r squared is 2 and tan theta is 1. Now, the fast and sloppy approach here would be able to say, okay, well, this means that r is the square root of 2. again, but it isn't, right? That the R is under no obligation to be positive. And this, it's tempting to say, okay, well, theta is pi over 4. Yeah, not really, right? And so the first observation I want to make is that if you do that sort of, fast and sloppy thing and you say, oh, okay, look, yeah, I know there's other values. Who cares? That I just need a pair of polar coordinates. I don't need all of them. I just want one that works. So I'm going to pick my easiest R. I'm going to pick my easiest theta, and I'm going to call those the polar coordinates. Well, guess what? That puts you over here. And that's wrong. Right. So this is the kind of thing you have to be worried about. These, polar coordinates, just not a situation where you can afford to be sloppy about that kind of thing. So what you have to do is be careful, right? And in particular, write down true equations, right? Then use that to understand the situation, and then write down your correct answer based on the, most of the work that was done by the algebra, and then the remainder that's done by your understanding. So altogether then, R squared being 2 means there's 2 possibilities for R. Tan being 1 tells me that there's, I'm going to say kind of sort of 2 possibilities, or there's a pi over 4 and 5 pi over 4. And of course, yes, there's also, you can go plus 2 pi as many times as you like, and you can go, same for the other one. But loosely speaking, I'm going to call this one, all these options, I'm going to call them pi over 4. Forgive me. Likewise here, 5 pi over 4. So we got all these different options, and then I just have to think it through. All right. Pi over 4 is that way. Which value of R, which ones of these values of R gets me to this point? How far do I have to go in the purple direction to get to this green point? And well, negative. And you see what happened there. The way that I was able to make that choice between these 2 possibilities came from understanding the picture, right? Understanding what's really going on. I got my options laid out by the algebra, sure, but the actual realization of what works comes from understanding the picture. Okay.
Professor,
Yeah.
would another option be to write this as the square root of 2 comma negative 3 pi over 4?
Yes. Oh, absolutely. The thing is, negative 3 pi over 4, there's 0. Negative 3 pi over 4 is like that. And I will observe, though, that that's the same direction as 5 pi over 4. So what that really is 5 pi over 4, and then minus 2 pi. So what you just described is just n equals -1. Yeah, absolutely, totally fine. And by the way, if you want to use negative 3 pi over 4 instead of positive 5 pi over 4, fine, no problem at all. There's nothing about the 5 pi over 4 that's the leader of that group of angles. Now, yeah, whatever, take your pick. I mean, myself, all else being equal, when I have a choice, I like positive. But yeah, so whatever you want to do is all good. Great question. Thank you.
So in the textbook,
Yeah.
they describe what to do depending on which quadrant your angle falls into.
Yeah, sure.
And I was kind of confused because they said when x is positive and y is negative, you take arctan and then add 2 pi. But
Yeah,
then when
I mean,
x is negative and y is positive, you add only just pi.
yeah, I mean, look, I mean, I've already made my sort of conscious choices of how much of what the textbook does that I want to spend class time on. So that's a great office hours question. But there's a lot of cases where the way the book does it, not my preference. So if you want to come to, well, I'll be happy to go through that with you in office hours. But for now, I'm just going to say, isn't this easier? I would encourage thinking of it this way. Yeah, totally. Yeah, there's going to be plenty of such situations. All right. let's see here. Yeah, so equations and polar coordinates, how do we draw pictures when we have an equation? Y'all are, of course, very accustomed to doing rectangular equations. And, how do we draw those pictures? So what if it's polar? R equals 3. I think it's pretty easy to persuade yourself that that's a circle, right? What this says is for every value of theta, no matter what theta you have, right? And all these different theta directions, go 3 in that direction. And that's just going to make a circle of radius 3. Now, if you hadn't noticed that, or if you just would prefer to rely on some algebra, a real slick move is to square both sides of that equation. That gives you r squared equals 9. Then recall that r squared is x squared plus y squared. And now you have what you might consider to be a more familiar equation. And if you want to say, oh yeah, and I know that that's a circle from high school algebra. So feel free to do that. I would argue though, between the two of these, I really think that one's simpler, right? And in fact, if you really think about it, think back to high school algebra. How was it that it was argued in high school algebra that this gives a circle? They made the observation that this is distance squared, right? So they effectively kind of sort of bring it back to something that's largely polar coordinates. So anyway, two different ways of thinking about it. Likewise, if theta is pi over 3, right? Pi over 3 is an angle about like that. That defines this direction. R can be plus or minus though. And so that really gives us, really gives us kind of all of that. So that gives us this whole line. And so if you want to say, there you go. I mean, it's just clear. That's, from the polar, that's what it is. Great. Do notice again, in this case, and this won't always work out, but it works out nice in this case. Take the tangent of both sides, and what we get is something that, again, can easily relate to rectangular coordinates. And so, again, you solve for y in this equation, bam, there you go. Same, that line that you're familiar with. Okay, again, is this somehow more legitimate, right? Not really. In fact, I argue that case could be made that really this is more directly relatable to the picture than the rectangular equation. But anyway, sometimes it's nice to be able to see it in rectangular coordinates. All right, now sometimes the algebra doesn't work, and sometimes you've got to just deal with, brute force point plotting in polar coordinates. So here's an example of that. R equals sine 2 theta, and try as you might, you're not going to have much success with trying to rewrite this equation in terms of rectangular coordinates. It doesn't work out nicely. So what you can do though is say, all right, well, I'm just going to think about what happens to, as theta changes, what happens to R, and just kind of go through it. So let's start off with theta being between 0 and pi over 2. And before we get into the algebra, let's keep in mind what this means. Theta being between 0 and pi over 2 means that we're looking at, well, there's 0. And then here's the angles between 0 and pi over 2, upsampling. Okay, well, if I take these values of theta, pop them into there and see what this function does. Well, it just, you got to plug in some values. Sine kind of does like that, right? And this starts at where we're taking sine of 0. It ends when we're taking sine of 2 times pi over 2. It ends when we're taking sine of pi. So it goes from there, it goes up and then down to there. This is what you might call the rectangular picture of what's going on there. So what does that look like polar? Okay, well, R starts at 0. Now, as theta increases, right? So there's my different values of theta increasing along, just like here's what it looks like in the XY plane as theta increases along. R gets bigger up into about the halfway point, right, where it reaches its maximum possible value. So as the angle turns, right, the R value, how far do I go in that direction, increases up to a maximum value of 1. And then it starts to decrease and makes its way. By the time I get to this direction, by the time I get to the end of this range of values of theta, I'm back to 0. And so here, let me color code this better. That's what it is doing in rectangular. That's what it's doing in polar. Okay. And then etc. So let's see here. Let me use different colors. I'll use orange here for now. Let's, pencil. We will use orange to represent the angles from pi over 2 to pi. Right. And so as I go along those angles, right, then here's what sine of 2 theta does for those values of theta now. And what it says is, well, R starts at 0, then it becomes negative, right? Oh, let's see here. Let me draw my lines again for these values of theta, right? R starts at 0, then becomes negative. At the halfway point, makes it all the way around to -1, and then comes back up to 0. So starting at 0, we kind of knew we were going to be there. But in this direction now, right, as my angle moves a little bit beyond, in this direction, I've got to go a negative R. And so that puts me down here. And then etc. By the time I get around to the halfway angle, I'm all the way over to -1. And then as the angles continue in that direction, they start to increase back up to, and by the time I go going that way, I'm back to 0. So you can kind of plot that out, trace that out too. These angles have me doing that. Okay, so it's just direct sort of plotting what's going on. We're using what we understand about the rectangular picture to just do that in polar coordinates, and that tells us what it looks like, in the XY plane. And so all together, let me kind of get rid of a lot of this stuff. We've got a big picture there. All together, what this curve does is it starts at the origin. It goes like this. And we've already sort of empirically observed to that point. And then I claim it keeps going, and it comes around that way. And then it comes around this way, and then back to the origin, and then it just keeps doing that loop. It's like a freeway interchange kind of a deal. Okay.
Are we gonna need to know the order of the petals that are made, or are we just gonna have to know the shape that it makes?
Oh, what you need to know is how to analyze a question like this and figure it out. So you should not be thinking of this as what do you need to memorize. The point is you need to understand the process of reasoning it out. So I'm not going to ask you a question on the exam that'll say, what was that picture? You remember this example from class, show me the picture, right? The question is going to be, I'm going to give you something totally different. And you're going to use these methods to then figure out the totally different picture that totally different algebra describes. Does that make sense?
Yeah.
And so, by the way, this has got a name, and it's some French sounding name, I think, probably. I don't know. But the point is, I don't care about that. What the label is, I'm not in that business. But the argument, the way to think about it is the point. Yeah, great question. Okay. All right, here's another example. This is a slick one. This It's tempting to square both sides because that would turn r into r squared. But instead, multiply both sides of the equation by r. And then it also turns the right side into something recognizable. So that gets us to that point, and now we're in rectangular coordinates, and it becomes an algebra 2 problem. So it's a slick move. I didn't think of this. Someone showed me this when I was learning this for the first time. And so again, it's not your job to have thought of this super slick move the first time. It's your job to remember the slick move now that I've showed you. Okay. Oh, and on this example, I also wanted to point out, oh, I guess I should point out that the answer, of course, is recognizably a circle. Where you can infer the center and the radius from the algebra. But I want to point out there's another little bit of algebra in here that I think a lot of students are maybe a little sort of shaky on, but this turns into that. And then somehow, right, the decision got made to add a fourth to both sides of the equation. And why did I add a fourth? Well, the reason I added a fourth to both sides is because that then turns this into a perfect square, which is necessary to get to the punchline, right? So this is an old algebraic technique called completing the square. And a lot of students, honestly, myself included in high school, saw completing the square in the context of solving quadratic equations and were then misled and told, myself included, right? And told, yeah, so you don't really need to know completing the square because you can use the quadratic equation. Well, that's bad. I have nothing against the quadratic equation, but it's not accurate to say that the only purpose of completing the square is to solve quadratic equation. It just isn't. Completing the square is a useful algebraic move. And you see here, for example, I didn't solve for anything. And yet completing the square was the essential trick to allowing me to rewrite the way I needed. So make sure you're good with completing the square. And if you're not, you can Google it. But it's an unfortunate casualty of high school algebra that's all too often sort of left out anyway, reasons based on misunderstanding. Okay. All right, now the last one I'm going to show you, this is actually even easier. Instead of moving from polar to rectangular, what if I want to move from rectangular to polar? And the good news here is just plug in known equations, and it almost always just kind of falls in your lap. So well, correction, very often it just falls in your lap. So you take this equation, for example. If I want to know what this looks like in polar, and by the way, we'll be doing this a lot when we start doing integrals in polar coordinates. It'll be later on. Well, multiply it out. And then just take advantage of the fact that, well, I know what x squared plus y squared is. It's r squared. I know what y is. It's r sine theta. You just plug that in, and lo and behold, we're now all polar, and there's the resulting polar equation. Yeah. Okay. For whatever it's worth, I do think these two equations here, if r is a multiple of cosine, or if r is a multiple of sine, being as they are circles, and being as it is that the world is full of circles, right? I mean, there's a lot of circles in the world. I think these ones are good to make sure you have right on the tip of your tongue that this one, this kind of a picture, well, it's going to come from an equation like that. And this kind of a picture, well, it's going to come from a polar equation like that. So these I want you to have on the tip of your tongue. But arguably more important, though, is the method. All right. Cylindrical coordinates. Good news. Cylindrical coordinates are pretty much just polar coordinates. You have a point in space. We're in 3 dimensions now. You can just drop down to the projection in the XY plane, and in the XY plane, you just do polar coordinates, r and theta. And then the z coordinate, Well, yeah, just hang on to that. So a lot of people call this actually polar coordinates in space or polar coordinates in 3 dimensions or something like that. That's reasonable, right? Polar coordinates in 3 dimensions or polar coordinates in space. That's kind of what it is. That said, it is more common to call it cylindrical coordinates. I'll also point out that fewer syllables. I encourage calling it cylindrical coordinates. And if you need another motivation to call it cylindrical coordinates, this, what you might call the most simple equation that you can write down in this coordinate system always makes cylinders. So that's why they call it cylindrical. Okay. All right. So I guess I should recognize then that, all the formulas from polar still true. And so it's like I say, it's pretty much just polar coordinates. So there's not much more to say other than a few examples. Spheres, if you want to write those in cylindrical coordinates, it's easy to do. You just rewrite the X and the Y in terms of R, and everything here is cylindrical. So this is the cylindrical equation. Here's a weird one. How do we understand this example? What I would point out here is, and I always be on the lookout for this kind of thing, it can be really useful, but notice in this equation here, there's no thetas. And if there were a theta axis, we could then say, oh, okay, well, then this has got to be parallel to theta. Well, there is no theta axis, so we can't use it in that way. But what I can say is, well, what that means is no matter what value of theta I pick, it doesn't make any difference in the equation at all. Geometrically, that would mean no matter what theta plane I pick, right? These slices here, or these half planes hinged on the z-axis. They all represent, well, just different values of theta. And the equation looks exactly the same in all of them, right? So another way to say that is that this is a rotation around the z-axis. Has to be a rotation because all the cross sections look exactly alike. So pick your favorite value of theta, whatever, and for whatever value of theta you pick, of course, z equals kr is just a line. And so what happens when you take that line and rotate it around the z-axis? Well, you get a cone. Okay. So pretty simple argument there. Nice conclusion. Let me pause for questions. Okay. Yeah, and I'll point out, as I have written here in the notes, don't forget about the fact that R can be negative. So a lot of people make the mistake, the following would be wrong. A lot of people would say, oh, well, this means that z equals k square root of x squared plus y squared. And you can see there it is. I'm playing fast and loose with square roots and implying that R has to be positive, as that symbol indicates. That symbol means positive. And of course it doesn't. R can totally be negative. That means that's wrong. Okay. Okay. Let's see here, moving along. We got like 2 minutes left. Yeah. This is annoying, but this is a reality that I ran into this problem a lot when I was in college, and you probably will too. There's a lot of problems where there's more than one radius involved in the question. And so, for example, if you have a sphere, well, the sphere has a radius. That sphere might have several cross sections. they all have radii, right? There may be a sphere and a cylinder in the same question. They both have radii, and all their cross sections have radii. There's a bunch of different things that you could reasonably want to talk about that can be described as radii. So the problem that you're going to encounter is that you're going to reflexively use R as a radius to represent whatever a certain radius is. And you can't do that because R is no longer just a free letter of the alphabet that you can describe as whatever you want. No, R is now one of our coordinates, right? And so if you call R two different things, on the one hand, it's a coordinate, and on the other hand, it's a radius of a given cylinder or something like that. Well, that's confusion of variables. So be really careful about that. Good choices are to use just other letters, if that's the easy one. But capital R, right, retains that satisfaction of feeling like I'm calling it a radius, right? But of course is different from the little r. Okay. All right, and this is a pretty good place to draw the line for today. We're done for the week, today being Friday. So I hope everybody has a good weekend. Final reminder, don't forget homework is due today, 11 p.m. And so make sure to get that turned in. Make sure your scans are legible. And there's a bunch of discussion about that on the Sakai side, of course. Yeah, you had Matthew, go ahead.
Can I ask you a quick question after the Zoom?
Yeah, sure, of course. Yeah, although the Zoom will keep going. Oh, and also, of course, you can come to office hours if you have a longer question. Yeah, but yeah, I'll stick around for a minute. See y'all later. Have a good one.
Thanks.
you.
Thank you.
Sure.
Thank you.
Yeah, what's up?
Yeah, I'm not sure if you had the chance. I sent you an email last night because unfortunately,
Oh,
number.
yes. No, I saw it, but I haven't had a chance to do anything about
Okay.
it yet.
Yeah, no rush. I'm just
Okay. Yeah. The reason I haven't answered is because I really have to look at all the data, all the numbers relating to class enrollments. But I've seen your email and I will
Okay.
respond very soon. Yeah.
Okay. Thank you.
No
Have
problem.
have a great weekend, I should say.
Yeah. Hey, you do.
Okay.
Hi, I had a question about scanning like the homework in.
Yeah.
Do you just want us to like scan all of the pages in? Like we did it in 218, or is it like sections? Like how does the scanning work?
I tell you what, let's go straight into the grade scope right now, and let's just see what it looks like. I'm confident that it looks the way it's supposed to look, and that'll make it easier for me to describe what I wanted to tell you. So let's see here. Are we in grade? Yeah, there we go. Let's see. Bray homeworks. Click on that. And homework 1. Okay. All right. Yeah. So you're going to see what it looks like on your end is probably going to be a little bit different because I'm an instructor, you're a student, and it's just got a different interface. But there are 5 questions in air quotes that I have to break it up in this way because Gradescope won't let me. The ideal would have been that each Gradescope question is an exercise, and then you upload all the exercises, and then only 5 of them get graded, and we can just ignore the others. But what happens is Gradescope says, "Well, you're not done grading," and it won't let us wrap it up. So it's super annoying. So what we're doing instead is for every assignment there will be 5 groups. As far as Gradescope is concerned, each one of these is 1 question, which works well because we're going to grade exactly 1 of those and exactly 1 of those and exactly 1 of those, etc. So basically you're gonna make a single PDF file. And by the way, a single PDF is fine. You don't need 5 separate PDFs. Single PDF file. And then when it asks you to identify which pages correspond to what it thinks of as question 1, then you're going to identify the pages that correspond to all of these exercises.
Okay.
And then likewise for the remainder.
So it's just like marking sections of.
As it turns out, in this case, it won't always be. We got lucky here that there were 5 sections, and it's easy to divide 5 by 5. But sometimes it'll be that there are 3 sections, and then the point is there'll be explicit indications of which exercises go into which one.
Okay.
Yeah, so just follow the instructions in the statement there, and it'll be good.
Okay. Awesome. Thank you so much.
Sure thing. Happy to help. Okay, Jaden.
Yeah, thank you. That was my question. Sorry, my mic wasn't working earlier because my headphones were connecting. But
Yeah, no problem.
Thanks for the
Not a
answer.
problem at all. Yeah, anytime. All right. See you.